Hi everyone, welcome back to the Reading Club. This is an ongoing series where I read papers on mixed integer programming and discuss their key ideas in simple language. And in today's episode, we are going to discuss large neighborhood search, LNS heuristics for mixed integer programming, which is taken from this particular paper, which is called Adaptive Large Neighborhood Search for Mixed Integer Programming, which is called ALNS. So this paper actually has a nice survey of different LNS heuristics that are used in mixed integer programming, and this particular new heuristic, which is called adaptive LNS, it actually combines all of those LNS heuristics that existed before this paper, right? So in this particular video, we are only going to discuss the other LNS methods, and in the next video, we will also look at the new version, that is the adaptive LNS version, which actually combines all of the other LNS methods, right? So this is kind of a nice overview of all the LNS based heuristics which we are using in MIP solvers. Okay, so first we will define some basics. Okay, so we are dealing with our standard mixed integer program, which has we are minimizing the objective, and let's just say ax is greater or equal to b, and x is between some bound L and U. Okay, and x, basically there are like three types of variables. Okay, so first of all, some variables are general variables. You can just say that are in rational variables. Let's say we have n variables in total. Okay, out of it, some of them are integer variables. So let's just say that we have ordered them in such a way that first all integer variables are there. So this part of variables are integer variables out of all total variables, and out of all these integer variables also we have one more special type, which is binary variables, right? So that only can take 0 and 1 values, right? So these are basically take all values in integers, and these are all the remaining variables can take all the rational values. Okay, so this is the basic setup, and the large neighborhood search basically work with some sort of an auxiliary problem. Okay, so auxiliary problem, and pretty much all of these constraints are same, but sometimes we can modify the objective, and some we can sometimes add some of one or two constraints over here, and that's pretty much it, right? So the if the typical feasible points are in SP, then we are basically will be searching from our SP intersection some neighborhood n. Okay, so we'll see different types of neighborhood in a minute, but that's the basic idea, right? So we have a set of all feasible points which is defined by this, and also like this integrality requirements if there is, and we on top of that will define some neighborhood, and sometimes we'll modify the objective. Okay, so that's the idea behind auxiliary problem. Okay, so mostly we'll be looking at a particular type of neighborhood. It's called fixing neighborhood. Okay, so basically n fix. Okay, and what it does is basically it will fix all the variables which I give, right? So which are in set m, which is m basically will be a subset of 1 2 up to set of all variables up to n. So set some variables it will fix, and in fact it doesn't even need to fix all the any of the continuous variables. So this can be also an int. Okay, so some of the integer variables it will fix it to some solution value that I provide x star, right? So basically xj equal to xj star for all j in m. Okay, so that's the thing. Like all the other variables are free, they can like take any values that they want. That's the standard fixing neighborhood. Okay, and there is also something called an improvement neighborhood, which is kind of also important. We rarely use it, but yeah, I think it is kind of used in some cases. So it goes like this, improving. So it's basically, let's say we have an incumbent solution, x, I, and c, and we want to improve it by delta. Then all we have to do is that we have our old objective, which is associated with It's basically C transpose X incumbent, and so we can do our old objective. And so anything that is better than all objective, it's kind of something that is improving, but we take it further a step and we'll also consider the dual bound. Okay, so the idea is that already dual bound is obviously going to be smaller than this because we are minimizing. So both of them are basically smaller than the old objective, or smaller or equal to. So we are going to put 1 minus delta weight on this one and delta weight on this one, and the new objective should be less than equal to this entire quantity. Okay, so that's like the improving the incumbent by delta. So that's improving objective. Let's just call it an objective. So sometimes we don't fix anything, but we can just have this part where objective should improve by this much, and that's also kind of a neighborhood. Okay, so and yeah, the last part is that matching set we have to define. So if we have a bunch of solutions, let's say x1, x2, not necessarily feasible or integer feasible solutions. They can be completely infeasible, right? So up to xk. Right, so the matching set is basically a set of all indices in which they all take the same values, right? So if there are values in which xj equal to xj, let's say I of them is same as xj for all of them, let's say particularly for all of them it's 1. So this holds true for all I. In that case, we will put this j in our matching set, right? So it's kind of denoted as m equal to and then this set of solutions that we are looking at, right? So the idea is that typically we will be fixing this matching indices where they are basically taking the same values in all those solutions to those same values. Otherwise, we'll keep things free. Right, so this basically wraps up the basics, and now let's start looking at the actual heuristics, LNS heuristics. Okay, so the first set of heuristics are going to be some or other variants of fixing neighborhoods, right? So we'll start with RINS, that is relaxation induced neighborhood search. So it is basically going to use our fixing neighborhood. What it is going to fix is so it will take two things, right? So one of them is my incumbent solution. It needs to have some incumbent solution, some solution which is feasible for the entire map, and it also uses the last LP solution. Okay, so these two solutions and anything that is matching in these two solutions, which is m equal to that we said, right? So everything that is matching, we'll fix it to those values, and we'll fix it to, let's say, it doesn't matter, right? So it can fix it to incumbent or LP. It's basically the same. So those indices are fixed, which are same in incumbent and LP, and everything else is free, and that's the rates, right? So if you just search over this neighborhood within some limits, then that's kind of good neighborhood to search for, right? It's a very successful heuristic. So notice that this part that is not actually a feasible solution of map, right? So LP solution is not necessarily an integer feasible solution. That may not belong to SP. Okay, so that's RINS. The next one is kind of extending the similar idea. It's called crossover. Okay, so here we are using one solution, and crossover says that we don't need to limit ourselves to one solutions. We can use up to k solutions, let's say. Okay, typically we you use 2 to 5 solutions. It depends on like what stage of solving you are and how hard your MIP is and all those things. There a bunch of hyperparameters are there everywhere, but the idea is that you can use multiple solutions. The same idea, like fix them, like find the matching set of all of this solution, x1, sorry, not here, to xk, and then yeah, just fix all of them to one of them, right? So this is n fix. Okay, so this just search over this neighborhood, and it's kind of similar to RENs, right? So, but there is no LP solution, and all of this are feasible solution. So here it was not feasible, LP solution was not feasible, but everything we consider over here are feasible. So obviously they don't need to be incumbent solutions, they can be any feasible solutions. We can take combination of any key feasible solutions and search over that neighborhood. So simple heuristic, it's called crossover. Okay, so the next one is mutation. So here we take our incumbent solution and fix randomly few indices in that, and that's our mutation, right? So mutation sometimes is kind of used along with the crossover. It's basically by the same set of authors. Those who basically found the crossover also found mutation, and so they you can basically combine these two heuristics as well. Okay, so this is again like very simple. And the last one, which is kind of it's not exactly going to use a fixing neighborhood, but it's kind of very similar to RENs. It's called RENs. Okay, so RENs is relaxation enforced neighborhood search, right? And so this one does not need any incumbent solution, right? So even if you have no solution, you can still use RENs. So the idea is that if I have an integer variable xj, right, and if I have its LP value, right, so I will seal it. Okay, seal, not floor, just seal, and say that it should be less than equal to that, and it should, I'll just floor it also for the lower bound xlp j, and I will floor it on this side, right? So if I have something that is taking 3.7, so I'll say that it should take values between 3 and 4, right? So original bounds could have been like say 0 and 10. Now I have restricted my bounds to 3 and 4. I'm just expecting that hopefully it will find a feasible solution, but I don't know where to round, right? I don't know whether to round upwards or downwards. So I just say, you know, both of these bounds are feasible, or both of these bounds are allowed. You can search over it, and we'll do some like MIP search, small level of MIP search on this. Okay, so of course there are more variations than this. So you can actually take add +1 here, -1 here, or things like that. You can do slightly more. You can increase the search space a little bit more. You can fix some integer variables and so on and so forth, right? So, but the basic idea is this, that this is the way you want to search, right? So these are our first set of LNS heuristics, right? So we'll look at some more. Okay, so in the next set of LNS heuristic, we'll be slightly changing the objective, or you'll be modifying the constraint sets. Okay, so first we'll start with a very famous one, local branching. Okay, so it's very simple. So let's first of all define a binary norm on our solution vectors, right? So x vectors. So it's basically, we'll sum from 1 to n binary, right? So we are not really interested in the entire solution. We are only interested in the binary parts, and just if it is 1, then it's fine, otherwise it's 0, right? So this is basically the binary norm. Technically it is not a norm. If you are a student and if you can figure it out why this is not a norm, it's kind of very easy argument, but if you can figure it out, then I'll encourage you to write it in the comments. It's kind of a small exercise for you. So it's basically like how many binary variables are taking value 1, and otherwise how many of them are 0, right? So that's the binary norm. And the idea behind local branching is very simple, is that let's say if I have an incumbent solution, right? So I want to keep my x between not so far from my incumbent solution as per the binary norm, right? This should be less than equal to some d max, some distance, right? So that's the idea. So let's say if I have a solution over here, then I'm basically, let's say d max is 4, then I'm basically allowed to modify up to 4 binary variables, 1, 2, 3, 4. And the fifth one, if I try to modify, then it basically falls out of the neighborhood, right? So that's the idea. Simple local branching. And why we are actually using binary norm in the first place, because if we use this binary norm, then this particular constraint, that binary norm should be less than or equal to d max, it can be actually represented as a linear constraint. Okay, it's a very simple thing to do, right? So if my in my incumbent, if my xj is 1, then I have to write 1 minus xj, and if it is 0, then I just have to write xj, right? So and just add all those variables. If say xj incumbent is equal to 1 and xj incumbent is equal to 0, right? So this is very easy. Just add all those xj, and then you have this kind of a simple linear constraint. I will again say that, so this has been actually extended to general integer variables as well, but it's for that this constraint can be represented as a linear constraint, right? So of course we will not be looking at binary norms, we'll be looking at integer norms or some regular norms. And the idea is that you have to actually introduce auxiliary variables for that, right? So again, like if you are a student, if you want to do some modeling exercise, then it's kind of a nice exercise that you can try to figure it out, how this constraint can be modeled as a linear constraint by adding some extra auxiliary variables. And that is for general integer variables, not just for the binary variables. Okay, so let me know in the comments if you can figure it out. Okay, so we'll move on from here to something very similar. It's called proximity search. So this is very similar to this local branching, except that here this is like introduced as the hard constraint, and in the proximity search we don't add this as a hard constraint. We just say that, you know, minimize x minus x inc binary norm. That's it. My objective is been changed. Original objective I'll throw it away, but or maybe I'll add it as some convex combination between this and the original objective, but mostly I'll be just using this one. So that's the idea, proximity search, and that's kind of very similar to local branching. Okay, then the third one is kind of even easier to understand. It's called zero objective, right? So its name itself should make things clear, right? So basically we remove the objective completely, and now my instance has been turned to a feasibility instance, right? So regardless of whether I have any solution or not, I can use zero objective. So if I have a solution, then maybe I will not use zero objective. I'll use zero objective, but I'll also add one constraint from that improvement neighborhood, right? So we remember that we can improve our neighborhood by delta. Right? So if we have an incumbent solution, then we can use we can add this constraint. Otherwise, we'll not add anything extra, and then we just look for any solutions that is feasible. Right. So that's another set of LNS heuristics that basically not just fix variables. In fact, none of this actually fix any of the variables. They basically modify constraints and objective. Okay, so we're going to look at one more LNS based heuristic. It is called DINS. Okay, so kind of name is kind of inspired from RINS. It's a distance induced neighborhood search. Okay, so previously we considered binary norms, right? And here we are going to consider x minus let's say x LP and integer norms I, right? So it's basically, instead of binary, we are going to go over 1 to n in all the integer variables, xj minus xj LP, right? So the difference, how far am I from my LP solutions, that's what I'm measuring over here, right? So basically it's the same thing as binary norm, but we are looking for up to all the integer variables. Okay, so the idea is that let's say if I have my incumbent solution, okay, let's say x enc, and let's say if my x LP, let's particularly look at jth variable, right? And if this this distance is, let's say, more than 0.5, in this case, I'm looking for a particular. I'm basically going to allow search space on this, right? So here is my LP solution. Here is my integer solution, and I'm saying that the distance between these two is this much. So I'm going to allow you to search in this distance plus on the other side same distance. Okay, so this is my XLP LP, and this is X incumbent. Right, so this is the area in which I want to search over. Okay, so how do we model this? It's kind of very simple. Xj minus Xj LP. This is less than or equal to Xj incumbent minus Xj LP. Right, so that's one sort of neighborhood. Right, so this, let's say, call it set of J. Right, so this are the set of capital J indices where this happens, where the incumbent solution is at least 0.5 distance more than the current LP solution. Right, so that's one part, but DINS actually combines a lot of previous heuristics as well. Right, so what we're going to do is first of all, so these variables are kind of left like given some search area, but other integer variables we are going to fix them. Fix other integer vars and going to fix them to X incumbent, like my best known solution. Okay, and now we are going to add something more, right? So we are going to add something from what we have seen before, crossover, and some part of rinse. So this is all inside DINS. Okay, so we have already fixed dealt with most of the integer variables, but now we are going to look at the binary variables. We are going to fix some more binary variables which are basically taking the same values in X LP, X root LP, so my LP solution, root LP solution, and say up to 5 solutions that I pick randomly, not necessarily incumbent solution, but up to 5. Right, I can also pick fewer solutions, but yeah, that's the idea. So if there is a binary variable which is not fixed here, which basically means its incumbent solution is 0.5 or more distance away from its LP solution, but it has been taking same values in LP and root LP and all of these 5 solutions that I have picked. In that case, I'm going to fix that binary variable. Okay, so it's kind of a combination of crossover and rinse, which is added to intersecting this neighborhood as well. And finally, we are also going to add our local branching constraint. Okay, so again, if you remember the local branching constraint, it's basically how many binary variables am I allowed to modify, and that is limited by D max. Okay, so it has like components from crossover, rinse, local branching, and some more distance induced neighborhood. Right, so this is basically the distance. Okay, let's also quickly discuss some more things that we didn't discuss. So some modifications lately that's been there in the literature. So what have we seen is a set of heuristics that we have seen, and some of them do not use incumbent solution, right? So which ones don't use any incumbent solution? So one of them was rinse, right? We do not need any feasible integer solutions, and the other one was zero objective, right? So this also doesn't need any integer solution, but other than that, pretty much everything needed some sort of feasible solutions, right? So they needed basically an incumbent solution, and they basically defined the neighborhood depending on where we are. So there is also an extended version of local branching, right? So that does not use incumbent solution. So the local branching constraint, that how far am I allowed to go from a given reference point, that's a local branching constraint, and that reference point does not need to be an incumbent solution, right? So it can be any infeasible solution as well, and you can still have this local branching constraint and search in a specific neighborhood from that reference point. right? So that's also kind of a nice thing to have. And there are some particular heuristics, LNS heuristics, which allow violation of constraints for our regular constraint, right? So ax equal greater equal to b, we can allow the violations, but in that case you need to penalize it, right? So penalize it in the penalty is basically introduced in the objective. So this is also something that we haven't discussed, but this is something that can be added to any of the heuristics that we discussed today, right? So what all other heuristics we discussed? We discussed rinse, crossover, mutation, DINS, local branching, zero objective, rinse, all those things we have discussed. So this is kind of a nice set of an overview for all the LNS based heuristics. And in the next video, we are going to use a particular one, which is ALNS, Adaptive Large Neighborhood Search, which basically combines all of these neighborhoods and figures out which one to trigger when, right? So that's, and what should be the size of the neighborhood and all those things. So this we'll be discussing in the next video. So hopefully this was useful. You learned something new maybe, and we'll see you in the next video. Bye.